Good morning, class. I'm having a little technical difficulties this morning, so bear with me for a minute. For some reason, when I log in to share my screen, it is changing my screen resolution. And maybe we just have to live with that for today. How you guys doing? Holly loves technical difficulties. All right, so I think I'm ready to go. So I want to spend one more day talking about topics and momentum, and I want to revisit one of the homework problems that is it's a really it's a challenging one, and we talked about it in recitation last Friday, but after class I realized that I had made a sign error and I didn't want to lead you guys astray. So we'll take a look at this problem again. It's the problem that's the ballistic pendulum, but the bullet goes through the paper. And so we'll talk about that, and then we'll do some concept questions. So how you guys feel about the election last night? It's crazy, isn't it? We might have two presidents for a while. Well, we just might have two presidents for a while. Yeah, we'll see how that turns out. Okay, so let's take a look at this problem. And I'll bring it up. All right. So here we go. So it's this problem right here where you have the bullet fired at a piece of paper target, and the information you're given is information about the relative velocity of the bullet pre and post. It says that the speed after passing through the target is about 53.6%, 0.536 v the initial speed of the bullet, and you're given information about how much kinetic energy is lost. It is not an elastic collision. So the change in kinetic energy is equal to this quantity. And that's where I made my sign error, because if it's a change in kinetic energy, it's a decrease. So when I set up my algebra, this should be a negative number when I set up my algebra. And then what you're asked to figure out is essentially, the big V is the final velocity of the paper. What is it relative to the initial velocity of the bullet? And what is the mass ratio? The mass of the paper to the mass of the bullet. That's what you're really asked to find here. These numbers are ratios: big V over little v and big M over little m. All right, so let's work on this and see if we can come to a conclusion. And the technical difficulties have returned. Great. All right, hold on a second. Yeah, it's still resizing my window. What the heck? Come on, you can do it. There we go. Yay! Ah, jeez. Technical glitches. All right. So I don't think I'll draw the picture again. Great. What the heck? All right. Yeah, all right. So now at least I can see the whole screen. All right. So the pre or before, we have the bullet coming in with speed little v. Let's do a little kind of like a cursive. Maybe I'll do a little cursive v so we can keep this straight, and it has mass little m. And then here's the target. And it has speed 0 and mass big M. And then after the collision, what the heck? Now the paper is moving with speed big V, and the bullet has some new speed called little v prime. And the information that we're given is, and this is little m. So the information that we're given here is that this post-collision speed for the bullet, v prime, is a fraction of what it started with. It's, for my case, 53.6%, or 0.536, the initial speed. All right, that's one thing we know. And the other thing we know is that the change in kinetic energy of the system is equal to 0. For my problem, 453 times the initial kinetic energy of the bullet, which would be 1/2 little m little v squared. All right, and the part I missed is if this is a change in kinetic energy, it's a loss of kinetic energy. Final minus initial is going to be negative. So that conceptual piece I just forgot to add on Friday. So there needs to be a negative sign here. All right, so with conservation of momentum, we can write out conservation of momentum, that the change in momentum is 0. We can write out an expression that looks like this, that the momentum before the collision is m times little v. And that must be equal to the total momentum after the collision, which is going to be m times little v prime plus big M times big V, the mass of the paper times its velocity. All right, and so one thing we can do here is v prime, go away, v prime is 0.536, so we can put that in there. We'd have little m, little v equals 0.536 little m, little v. V prime is 0.536 plus mv. And that takes us to, let's subtract the 0.536 mv from both sides, and we'll get 0.464 little m, little v equals big M, big V. Okay? I'll write that a little nicer. 0.464 little m, little v. Okay? And so conservation of momentum and the fact that we know the relationship between the initial and the final velocity of the bullet, v prime and little v, we can come up with an expression like this. So now let's turn our attention to, actually, let's do one more step here. I'm going to divide both sides by m little v. So that would give us 0.464 equals the mass ratio, and that's one of the things we're trying to find, big M over little m, times big V over little v, which is the other thing we're trying to find. The ratio of the velocity of the paper after the collision, big V, divided by little v, the velocity of the bullet, the speed of the bullet before the collision. All right? And so there's two unknowns in there, but I've written them as ratios. All right? But that's what we're trying to find. Big M over little m and big V over little v. All right. What about the fact that kinetic energy is lost? Okay, the change in kinetic energy is less than 0. Well, let's write out an expression for that because we know what the loss is. The problem tells us the system has lost 45.3% of the kinetic energy it started with. Jeez, I don't know why that keeps popping up. Which is 1/2 mv squared, little v squared. That's how much kinetic energy it started with. All the energy was with the bullet. So that's going to equal the final kinetic energy of the system, which would be the kinetic energy of the paper, 1/2 big M, big V squared, plus 1/2 little m V prime squared, the post-collision kinetic energy of the bullet. So that, in parentheses, is the total kinetic energy of the system after the collision, and we subtract from that what it started with, which would be 1/2 little m little v squared, the kinetic energy of the bullet before the collision. Okay, so now we can do a bunch of simplification here. We've got a 1/2 mv squared on both sides, so we can add that to both sides. And that will give us, let's make this a little smaller. So if I add the 1/2 mv squared, little v squared, to both sides, that's going to give me 0.547 1/2 m v squared equals 1/2 big M big V squared plus 1/2 little m. And then here, the V prime is 0.536 times V. The V prime is the initial speed, the final speed of the bullet, and it's 0.536 times the initial speed of the bullet. All right, so there's 1/2s everywhere. I can get rid of that. But what I'm going to do is, so then I got this other 1/2 MV. Go away. Don't know why that keeps popping up. This is weirdness today. So I can take this term and subtract it from both sides after I square it. And then I get another term. So that term is another term that has 1/2 mv squared. I got a 1/2 everywhere, so that will cancel. So if I do those two steps at once, I'll end with 0.259. I'll keep a bunch of decimal places here. 704 m little v squared equals big M big V squared. Now divide both sides by mv squared. You get 0.259704 equals the ratio, which is one of the things we're trying to find, big M over little m, times the ratio of big V over little v squared. So I have these two equations now, and I have two unknowns, these ratios. So one of the things you can do here is I can take this equation, call it equation 1, and divide this equation, equation 2, into it. So you would, if you do that, you see on the right hand side you have a m over little m, big V over little v, and then it's squared. So if I divide 1 by 2, I will be left with a v over little v on the right hand side. And on the left hand side, it's just the ratio of these two decimal numbers. So when you do that, you take 1 and divide by 2, equation 1, and divide by 2, what you get is 0.5597 equals big V over little v. So this is one of the answers. that we're looking for. All right, and then once we find that, we can plug it back in up here, and we can solve for that other ratio, big M over little m equals 0.8290. Okay, and we're done. All right, those are the two answers that we're looking for. All right, can you do this? Can you do this? Yes, of course you can do this. All right. I just wanted to go through that and make it clean because I forgot that negative sign in class on Friday. But now I think it's pretty clean, and now you have a record of that problem that you can use. So this homework is due tonight. Does anybody have any other questions about this problem set that's due tonight? It looks like, I looked at how you're doing this morning, and I was looking to see if there's any particular problem you're having difficulty with. It just looks like, the problems near the end of the problem set are more people have to finish those than the problems at the beginning. To me, that looks like a sequential thing. You're just working on the problems in the beginning first, but you're leaving the ones at the end for last. Isn't really an indication that you're struggling with those problems. You just still have to do them. Some people are completely done. Some people haven't started this assignment. So you got a couple hours here to get it in. All right. Not seeing any questions. All right, let's do clicker questions. All righty, here we go. We got I got the poll everywhere up and running, and let me just change. Come on. Nope. Yay! I found it. All right. So this is the poll everywhere poll. So pollev.com/JeffreyGroff336 or text your answers to JeffreyGroff336. Text JeffreyGroff336 to 37607 to join. All right. Oh, you guys still with me? I think you are. I just had a spinny wheel. All right, so pollev.com, JeffreyGroff336, or text JeffreyGroff336 to 37607. Text messaging charges may apply. All right, you ready? Let's, I'll leave that up for a second while I queue up the first question. Ooh, first question coming up in 3, 2, 1. Here it is. A system of particles is known to have a total kinetic energy of 0. Total kinetic energy of 0. What can you say about the total momentum of the system? It's positive, negative, 0, or you can't say anything. You can't say anything. What is it? Let's see. The poll is active. The poll is active now. Sorry, if you already tried voting, try again. I hadn't activated it. All right, we've got our first response coming in. pollev.com, JeffreyGroff336. Or text JeffreyGroff336 to 37607 to join in. Got 3 results, 4 results. We are counting votes quicker than they count them in Wisconsin, Michigan, and Pennsylvania. I saw today that they're calling in the National Guard to count votes in Wisconsin, and I'm thinking, really? Is our voting system worse than a third world country? What the heck? They have to hand transcribe votes that one scan in the Scantron. So they're calling in the military to do that. Oh boy. Democracy in action. All right, you ready to see what you got? So your poll, you guys like C. You guys like C, which is I got too many windows open here. You guys like C, which is the correct answer. Total kinetic energy is 0, and that means everything is at rest. Everything is at rest. Let's flip things around, all right? Let me clear out the responses in the poll, and it is open again. A system with particles is known to have a total momentum of 0. Does it necessarily follow that the total kinetic energy of the system is also 0? Yes or no? Yes or no? And the votes are coming in. The polling stations are open. So the votes are coming in. They're being tallied. Oh, it's very close. It's very close. We have a nail biter here. Oh wait, I just found a box of absentee ballots. Let me add those into the count. I'm sorry. Oh man. 38% to 63%. You guys prefer B, no. Doesn't necessarily follow the total kinetic energy is 0. And that is the correct answer. Because yes, it is possible that if the momentum is 0, the kinetic energy is 0. But it's not the only possibility, because momentum is a vector. So you can have two things moving in opposite directions, one with positive momentum, the other with negative momentum, and the total momentum can add to 0. But you have two things moving, so kinetic energy is not 0. So yes, you can have systems where kinetic energy is not 0, but total momentum is 0. All right. This gets at the fundamental difference between kinetic energy and momentum is that one's a vector quantity and the other's a scalar quantity. All right, scalars are just numbers. They add together. And actually, kinetic energy can never be negative. You can never have negative kinetic energy. You can only have 0 or positive kinetic energy. And that's a mathematical fact, because it comes from, it's calculated from mass and speed squared. So mass is always positive, and speed squared is always going to give you a positive number. All right, you ready for the next question? So far, not so bad. All right, let me find the next question here. Ooh, okay, so this is a similar question. Let me clear the responses here, and then here it comes. You ready? Boom. Two objects are known to have the same momentum. Do these two objects necessarily have the same kinetic energy? Two objects have the same momentum. Does that mean that they have the same kinetic energies? Magnitude. Magnitude here, people. Just magnitude. This isn't worded too well. All right. Did anybody vote for Kanye? He wasn't on the ballot in West Virginia. I don't know if he was in Maryland or Virginia. But, yeah, he wasn't on the ballot. Berkeley County was had a surveyor on the ballot, and there was nobody running for it. It was just on the ballot, but there was nobody to vote for. Oh, you could write someone. I wrote myself in. So if I get a couple votes, maybe I'll be the Berkeley County surveyor. Let's see. No. Oh, right. Overwhelming. All right. Unlike presidential election results in the United States, the results of this poll are a resounding vote of no. No. And yes, that is the correct answer. No is the correct answer. Kanye got 1,000 votes in Kentucky. Kanye. So the reason why is this true? So both of these quantities, look, both of these quantities, mass, momentum, and kinetic energy, depend on mass and velocity or speed. Mass and speed. Let's think mass and speed. Of course, momentum has a direction as well, but let's think mass and speed. The magnitude of the velocity. So what this question is saying is you have two things that have the same product, mass times speed. The size of that number is the same. Well, you can easily imagine a situation where that means, like, maybe you have a 10 kilogram mass moving at 1 meter per second, or you have a 1 kilogram mass moving at 10 meters per second. Both of those situations would result in 10 kilograms meters per second of momentum. All right. So then but how does that translate to kinetic energy? Well, in kinetic energy, it's depends on mass and speed, but the speed is squared. So the speed is going to matter more. So if you have 1 kilogram going at 10 meters per second, it's going to have a lot more kinetic energy than the 10 kilograms going at 1 meter per second. Okay. So this is a really interesting problem, and it's a conceptual thing that I really want you to understand, that the kinetic energy is squared. So I have, I'm going to come back to that one and that one. These are all so good. I want to find, there's a quantitative, here we go. Let's do this one next. All right, hold on, let me clear the poll. All right. Excuse me. All right. So here we go. It's a cannon that sits on a stationary rail car with a total mass of 1,000 kilograms. A 10 kilogram cannonball is fired to the left at a speed of 50 meters per second. And the question is, what's the recoil speed of the flat car? So you might need a piece of paper for this. But this is a conservation of momentum problem. It's a totally inelastic collision in reverse. Instead of two things coming together and sticking, you have two things flying apart. It's an explosion. So what's the total momentum of the system before the cannon is fired? 0. The total momentum of the system is 0. So after the cannonball is fired, the total momentum is still 0. You have the cannonball going to the left, let's call that negative momentum, and the cannon going to the right, let's call that positive momentum. Can you figure out then what is the recoil speed? Wow, we got 50-50 right now on the poll. 50-50. All right. I'll give you another 30 seconds. All right. Good. Okay. So here's the correct answer. And 0.5 meters per second to the right is the correct answer. And so you have these two objects, and the cannonball is going to have momentum of 10 kilograms times 50 meters per second, 500 kilograms meters per second to the left. So the flat car's momentum needs to be the same amount to the right. And if you know its mass, you can calculate its speed. Must be 0.5 meters per second squared, or 0.5 meters per second. So, here's a really clear example of an example where momentum is conserved, but kinetic energy is not. The cannon fires because there's an explosion of gunpowder inside the cannon, and that imparts energy on this system. But the energy is not imparted equally. I mean, you can look here. Let's actually calculate some numbers here. I'll do it and tell you. So the flat car is going to have a kinetic energy equal to 1/2 times 1,000 kilograms times 0.5 meters per second squared. That's 125 joules. So after this cannon fires, the cannon will recoil with 125 joules of kinetic energy. 125. All right, now the cannonball. The cannonball is going to have a kinetic energy of 1/2 times its mass, 10 kilograms, times its speed, 50 meters per second squared. So it's going to have 12,500 joules of kinetic energy. Okay, so the energy that's created in the system is not distributed equally between these two objects. Most of the energy is imparted on the cannonball. All right, a very clear example of the fact that energy and momentum are not the same thing. They're definitely not the same thing. All right, how are we doing in time? We got 20 more minutes. All right, this is a good one. All right, I'm clearing the responses. You're ready to go again. A bowling ball and a ping pong ball are rolled toward you with the same momentum. If you exert the same force on each one, which takes a longer time to bring to rest? All right, this is a, you see the equation there? That's the equation for impulse, change in momentum, which is also a force exerted over an interval of time. All right. What do you think here? Okay, all right, so I'm getting some of you, your favorite answer is B, same time for both, but I got a few answers for A and C, the ping pong ball. So the correct answer is, drum roll please, B, same time for both. Okay, so I think, you approach this mathematically. The force, it says the force to slow these moving objects down is the same, and so if you take that impulse expression and solve for force, you get force as change in momentum over change in time. So if those ratios are the same for these both these cases, and they both start with the same momentum and are brought to rest, then they both have the same F and the same delta P, so they must also have the same delta T. So which follow-up question here, put it in the comments. If the ping pong ball and the bowling ball have the same momentum to start, which one is traveling faster? Which one is traveling faster? You know who the biggest loser was last night? You can put your answer in the comment. Who was the biggest loser last night? I don't see nobody put anything in. Ping pong ball. Thank you, Katie. Thank you, Katie. So the ping pong ball must be traveling a lot faster because ping pong balls are much less massive than bowling balls. And if both these objects had the same momentum, m times v, then ping pong ball must have a much larger v because it has a much smaller m. Thomas, my sleep schedule is the biggest loser. That's great. All right. Anybody else have an idea I got like a serious answer who the biggest loser is, but from last night's election. But let's see, the biggest, like the TV show. What was the biggest loser of this election cycle? All right, let's see. I'm going to queue up the next question here. All right, so here is a question about an explosion. So this is like the cannonball problem. Uranium nucleus undergoes fission and splits into two fragments, one heavy and the other light. Which fragment has the greater momentum? The greater momentum. Maggie says the American P. No, I think the American P. I've never been prouder of our country than I am right now. I think that, I mean, I think we're in for a few months of some pretty maybe some serious uncertainty, but voter turnout was enormous. What better way to reaffirm our commitment to democracy than to just have huge voter turnout? But back to this question. Oh wait, I think the poll's open. Let's see. And I'm not even sure what the final turnout numbers were, but they see, from what I saw, I mean, I waited in line for 2 hours to vote yesterday morning, and I've never waited that long before. That's yeah, it's pretty crazy. So I don't know if turnout was like that everywhere, but my dad up in PA said turnout was crazy large. You guys like C, both have the same momentum. Correct. Great. You guys got this. You're going to ace this next test. The uranium nucleus at rest undergoes fission and splits into 2 fragments. So the key here is the total momentum of the system is 0. So if they split into 2 fragments, the total momentum is still 0. But they're traveling in opposite directions, so they must have the same magnitude momentum, just in opposite directions. But the follow-up question's a little more trickier here, so let me cue that up here. All right, here it comes. Wait, let me reset the poll. All right, and here it comes. Oh, wrong one. Hold on. There we go. Yay. All right. Which one has a greater speed? The heavy fragment, the light one, they both have the same speed. All right, well, I answer this. So my vote for who was the biggest loser in this election for the second time in a row, the pollsters. The pollsters. Let's see. I think you're good. You're voting. I'll give you another minute, okay? Got a couple votes in here, but I'd like a few more. All right, so you guys, good. 71% of you picked the right answer, which is B, the light one. The light one must have higher speed. All right, it has less mass, so if they both have the same momentum, if you have less mass, you must have more speed to compensate. All right. Let's not do that one. That's the same situation. Yeah, let's do this one. Nope, this one. All right, let's take a look at this one. Let me clear the poll. And so I had a frightening thought this morning too, which maybe I'll share with you before we end here. And about the state of our existence. All right, I'll share it with you before we end here. The 2 slide, they stick together. So this is a totally inelastic collision, and the momentum of the system is conserved. So you start out with momentum that's all with one object, and then they collide and stick together. You got this. If this is throwing you for a loop because the mass isn't given. They're equal, which is all you need to know. But you can just make up a number, and certainly the answer doesn't depend on the specific value for mass here. So if each of these m's is 1 kilogram, then the system starts out with 10 kilogram meters per second of momentum. After they collide and stick together, now there's a total mass of 2 kilograms, but there's still 10 kilograms meters per second of momentum. So how fast are they going? Good, you got this. All right. All right, so let's take a look at the answer here. E, 5 meters per second. The speed must be halved because the mass was effectively doubled. So if momentum's conserved, mass times speed, mass times velocity, and the mass is doubled, the speed must be halved. All right. Do I have... Oh. Darn it. I already showed you the answer. All right, well, let's just talk about this one. This is a good question, too. I really like this one. All right, here we go. So I already showed you the answer. I'm sorry. A small object collides with a large object and sticks. Which object experiences a larger magnitude of momentum change? And it doesn't matter what that first sentence says. It doesn't matter. It could say a small object collides with a large object and bounces. A small object collides with another small object and sticks. Two large objects collide with one another and bounce off partially. It doesn't matter what it says. If we are assuming that there's no external influences on this collision, no external forces, momentum is conserved, which means if one object experiences a positive change in momentum, the other one will experience a negative change in momentum, which is exactly the same size, the same magnitude. So C is always the correct answer. Both objects experience the same magnitude of momentum change. So this is synonymous. Don't let the words throw you for a loop here. Momentum change is synonymous with what? Can you put it in the comments? What's another name for change in momentum? Can you put it in the comments? Notice that this, here's a hint. This problem is a lot like the conceptual questions about interactions governed by Newton's third law, action, reaction, force pairs, and that's not coincidence. That's because this phenomenon of momentum being conserved is a consequence of Newton's third law. Equal and opposite action, reaction forces leads to equal and opposite magnitude momentum changes. So what is, does anybody get my drift here? What's another word for change in momentum? There you go. Thank you, Katie. Thank you. Impulse. Impulse. So, these are the kinds of things that you should be thinking about when you're studying for the exam. Impulse. Both objects experience the same impulse. The same impulse. All right. I might have one more here. This one's easy. Two objects collide and bounce off of each other. Linear momentum is definitely conserved, or this is a poor question for an exam. Conserved only if the environment is frictionless. So both of those answers would be correct. Two objects collide and stick together. Kinetic energy is definitely not conserved. Definitely not conserved. All right, that's related to things that we talked about. Hey, this looks familiar. Lying in bed. center of mass question. I probably won't ask you any questions about center of mass. That's and this question you can answer from the simulation you did a few weeks ago. But this, yeah, let's not talk about that one. All right, gang. So that's it for today. So you want to hear my scary thought? So the last few elections, at least these national elections, are the ones which are driven by, you think about it, like, the local elections probably matter a lot more because of, like the county commissioners, for example. They're like setting policy that directly affect our streets and our tax rates, our local tax rates. And it's like really hard to find information about them. But you think about, like, how mass media makes money these days. It's really click driven. You're bombarded with ads. So anything that gets your attention is going to be money making, right? I mean, you guys know this. But so here's the thing, like these national elections for president, I was thinking about this, that is there a reason that they're split like almost exactly 50-50 in according to the rules. When I mean 50-50, I mean the rules that lead to you winning, which is the electoral college, not the popular vote. And so when you have a distribution like this, what is this doing? It's like optimizing the system that we have, which is a two-party system, because the person with the most votes wins, and it's optimizing it for a situation where you're creating the most polarity. There's this concept called entropy, information theory, entropy, and a distribution that has the most entropy is one that's uniform, where you have the same amount in two different categories. And then I started thinking, well, what is driving this equilibrium process? And we like to think that it's like free will and like, truth and knowledge and all that. And I thought, well, what if it's just the optimization of an algorithm that's driven by artificial intelligence? So, artificial intelligence is something I have some knowledge about. How does a neural network work? By finding patterns and then optimizing around those patterns. And I thought, well, what if what's driving this, the driving force behind this drive toward equilibrium partition and creating this polarity between these two groups in order to drive, is that the systems that are behind all of the social media and traditional media systems are now driven by artificial intelligence, which are making the decisions for us. And it's kind of like a situation where no human really knows what the algorithm is about. So these artificial intelligence algorithms are sort of already have free will because they're doing things that no person understands. And so the scary thought I had was, what if the AI is already in control? Could be. Free will is a myth. Well, free will, you could say that like it's just I don't know how you guys, free will, you can talk about it like biologically, that like, we are like squishy computers, right? We're just like liquid filled computers. And so if you know the initial state of a computer, you can figure out where it's going to be in the future. And so then free will just boils down to uncertainty. There's complexity. So our perception of free will is just that we don't have the ability to understand all the complexity. So you could say it that way. But if you guys ever you guys know C.S. Lewis, the author, he writes about free will sometimes, and he's a religious guy, a Christian background, and he's got some interesting takes on that, which kind of are unexpected, because it's sort of like, in his perspective, free will is an artifact of our existence in the presence, where the reality of the world is that time is a figment of our existence, and the reality of the world is that sort of everything exists all at once. And so free will is this manifestation of this fact that we exist in the present moment, and for us there's a past and then there's a future, and reality isn't like that. All right. Holly's going to call herself a squishy computer from now on. I like this. I've heard people refer to humans as meat computers. That's gross to me. Squishy computers. We got squishy computers up here. Yes. All right. So that's enough for today. Enough philosophy for today. So I will see you guys on Friday, and we're going to start talking about rotational mechanics on Friday. Okay. This will be revisiting a lot of the material we've already learned, but looking at it from a new perspective. And this stuff won't be on the next exam. The next exam is just momentum, but it will be on the final exam. All right. So I'll see you guys on Friday. Bye-bye.